All right, let's get right into it. Today, we're going to take a peek under the hood of string theory. We're going to look for the recipe, the actual mathematical blueprint that shows how one single fundamental thing, this tiny vibrating string, can somehow become every single particle we see in the entire universe. That's the billion-dollar question, right? How can one thing be the source of all this variety? You've got an electron over here, a photon over there, a quark somewhere else. How? It sounds kind of impossible, but string theory offers an answer that's, it's both mind-bendingly complex and just beautifully simple at the same time. Okay, so here's the core concept. Think about a guitar string. It can play a whole bunch of different notes, right? A low C, a high G. It all depends on how it vibrates. Well, string theory says it's the exact same idea for fundamental particles. A string can be a different particle based on its unique vibrational pattern, its own special song. Its mass, its charge, everything comes from that vibration. And that's where the real challenge kicks in. If you want to understand the song, you first have to write down the sheet music. Physicists need a rock-solid mathematical way to describe any possible motion of this string as it's zipping and wiggling through space-time. And trust me, that is a way harder problem than it sounds. So, to get a handle on this super complex motion, physicists came up with a really clever mathematical trick. Instead of trying to describe the whole complicated wiggle all at once, they figured out a way to split it into much simpler, easier to manage pieces. And this trick involves something called light cone coordinates. Now, don't get hung up on the name. What's really important here is what it lets us do. It's like putting on a pair of special glasses that lets you see the string's chaotic-looking vibration for what it truly is, just the combination of two way simpler waves. And here's the result. It's awesome. The string's total motion is just the sum of some waves traveling left and some waves traveling right. It's like two simple melodies playing at the same time. On their own, they're super easy to describe, but you put them together and they create this rich, complex symphony that is the string's total movement. So now that we can split the wave, we suddenly have a way to write down a master recipe. We can create a formula that can build literally any possible vibration, any possible note from a set of really basic fundamental ingredients. It's a lot like music. Any complex sound, like a chord on a piano, can be broken down into a sum of simple, pure notes, what we call harmonics. String theory does the exact same thing, just for the shape of a vibrating string instead of a sound wave. And here it is. This beast is called the mode expansion. I know it looks super intimidating, but just think of it as our ultimate recipe. It's basically saying that any possible shape of the string is built from just a few key ingredients. So the real key here is to just understand what those ingredients are. Let's break it down real quick. You've got some terms for the string's general motion through space. That's its position and momentum. Then there's a term for the string's tension, basically how stiff it is. But the most important ingredients, the real secret sauce, are these last ones, the alphas. These are called the oscillator modes. These oscillator modes, this is the heart of the whole recipe. The best way to think of them is like a series of volume knobs for each harmonic of the string. You've got a knob for alpha 1, one for alpha 2, one for alpha 3, and on and on. Want a little bit of the first harmonic? You turn up the alpha 1 knob. Want a whole lot of the fifth harmonic? You just crank up the alpha 5 knob. By choosing which knobs to turn and how much you turn them, you compose a totally unique vibration, which means you create a unique particle. Okay, so we've got a recipe that can describe any mathematical vibration you can dream of. But here's the catch. Not all of them are physically possible. A real string has to play by the laws of physics, and these constraints actually rule out a whole bunch of those vibrations. So let's see what these rules are. To enforce these rules, physicists use this amazing mathematical tool called the Virasoro operators. Each one of these operators, labeled L sub n, is a really complicated mix of all those oscillator volume knobs we just talked about. They're basically mathematical bouncers at a club checking if a vibration is physically allowed to exist. So you take all those volume knobs, all that information about the vibration, you plug it into this incredibly complex Virasoro operator, and the physical rule they have to obey, the deep physical constraint that comes from the theory itself, it all boils down to something that is just shockingly simple. 0. That's it. Every single one of those complicated Virasoro operators has to equal 0 for that vibration to be a real physical state. Out of this infinite ocean of mathematical possibilities, nature only allows the ones that perfectly, magically balance out to nothing. It's amazing. So you might be thinking, why did we go through all that trouble with recipes and knobs and rules that have to equal zero? Well, because this is where everything connects back to reality. These abstract mathematical rules have a direct physical payoff. They tell us the mass of the particle that the string is representing. And hey, don't just take my word for it. We can see it right here in the text. It states, crystal clear, that two of those constraints, the L0 and L0 tilde ones, directly give you the mass of the string based on those oscillator modes, based on which volume knobs you turned up to create the vibration. And this, right here, is the punchline. The mass of a particle in string theory is literally just the total energy packed into its vibration. The more you crank up those oscillator volume knobs, the more energetic the vibration gets and the heavier the resulting particle is. So the recipe for making a particle with a specific mass is perfectly clear. First, you pick a vibration pattern. You do that by turning up the volume knobs for the different oscillator modes. Then you just add up the energy from every single one of those active modes. And that grand total, that is the mass of your particle. And there's one final, really crucial rule called level matching. Remember how we split the string into left-moving and right-moving waves? Well, the theory demands that the mass you calculate from the left movers has to perfectly match the mass you calculate from the right movers. It's this beautiful internal check that just makes sure the whole theory holds together. So when you really step back and look at it, the message of string theory is pretty profound. A fundamental particle isn't some tiny, boring little dot. It's a rich, complex resonance. It's a song being played on the fundamental instrument of the universe. Think about it. An electron is just one specific, beautiful chord. A photon is a different chord, a different song, but it's played on the exact same string. All the matter and all the energy that we see around us is just a different note in this unbelievable cosmic symphony. So we've built this amazing classical picture. We have the recipe for what a string is and how it gets its mass. But we all know our universe is quantum. So the really critical next question is, what happens to this beautiful, elegant recipe when you throw in the unavoidable fuzziness and uncertainty of the quantum world? Because that's where things get really interesting.